Good morning, everybody. Welcome back to Abstract Algebra. Plan for today, cyclic groups, continued. Office hours. On Monday, I will have my office hour before class, but I will not have my Monday afternoon office hour next week because I have to go sit in on another professor's class and stare at them the way you stare at me and make them feel uncomfortable for a change. So I'll apologize for that. Homework. So homework 2 is due tonight. Homework 3 will be posted later today or tomorrow, and it will be due next Friday. We'll have some questions about subgroups and a couple about cyclic groups on it. Is the plan. Proving things like the rational numbers do not form a cyclic group. Any questions or comments before I do the joke of the day as we get started? Where do they put mathematicians who commit crimes? They put them in a prism so that they can be with all the other convicts. Okay. So you may remember from Wednesday's class, we talked a little bit about cyclic groups. We said that a group is cyclic if it can be generated by a single element. So like the integers, for our example, could be generated by 1 or -1. Since the entire group of integers can be found from just the number 1 by adding 1 to itself enough times, or by adding 1 inverse to itself enough times, where 1 inverse was -1. If you added 1 to itself enough times, you get all the positive integers. If you added 1 inverse, or -1 to itself enough times, you get all the negative integers. And then if you take 0 copies of 1, which just gives you 0, that gave you the entire group of integers. And so the integers were a cyclic group under addition, and it could just be generated by a single element. Whereas all the other groups we've looked at so far, the dihedral groups, the matrix groups, etc. All of those were not cyclic, you could kind of say. And we're about to come up with an example of a finite cyclic group at the end of class last time. We had talked a little bit about modular arithmetic, which is based on this theorem that says that given any two integers a and b, there exist unique integers q and r, such that a is equal to qb plus r, where r has to be between 0 and the absolute value of b, where basically this q and r were what you get when you were to do division. A divided by b, q was the quotient, r is the remainder term. And we talked about how you could do modular arithmetic by defining the binary operation a mod b is equal to the r term that this theorem guarantees has to exist and be unique. So a mod b is equal to this r term, and we define two operations, addition and multiplication mod n, where a plus b mod n is just you add a and b and then do mod n. Find the remainder when you divide by n. And similarly, a times b mod n is you can multiply a and b normally, and then just take the remainder term when you divide by n. You take ab mod n. Where, as we mentioned yesterday, you could also equivalently take a mod n and add it to b mod n. Or you could just take a mod n and multiply by b mod n. Questions about any of this before we get started with the new stuff for today? We're going to be using these operations to define a couple group structures. Okay, so here's our first example. Z mod nz. How you say that out loud? Which we're going to define to be the set of all integers 0 up through n minus 1. It's basically a set of n integers, n if you include 0 and don't include n itself. And I claim, no matter what your n is, this is always going to form a group under addition mod n. meaning if you just take this set of integers, then I claim that if you add integers from this set together, mod n, then we have all the nice things we need to have a group. We have closure, we have associativity, we have an identity element, and we have inverses. So let's take a look at an example. Let's take a look at Z mod 6Z. So as a set, this is just going to be the set of integers 0 through 5. So if we were to take, say, okay, give me an integer from this list, from this set.
4.
Okay, if we were to take 4. Peter, give me an integer from this set.
3.
If we were to take 4 plus 3, and we were to do our group operation, which is going to be addition modulo 6, then that means, by definition, we're going to add the two integers, 4 and 3, which will give us 7 mod 6. And which group element will this give us? If we were to take 7 divided by 6, what would the remainder term be? Okay?
1.
It's going to be 1. So we added this one, and we ended up back over here. So this is kind of going to be how our group operation works. You just take two integers from this set, you add them normally, and then you just mod out by n. In this case, n equals 6 in the end. What's the identity element in this group? I claimed it's a group, so it has to have an identity element. Something that if you were to add this thing mod 6, it changes nothing.
0.
Yeah, the identity element, just like with the regular integers, is always going to be 0 in any z mod n z. No matter what your n is, you'll always have 0 in the set, and that will be your identity element. Because if I were to take 4 plus 0 mod 6, well, that's just going to end up being 4 mod 6. And anything in this list mod 6 is just going to be itself. Because these are already kind of terms that are between, these are already all numbers that are satisfying this equation. That they're between 0 and 6, including 0, not including 6. Let's see if we can find some inverses. I'll do the hard one. 0 is going to be its own inverse, because in any group, the identity element will always be its own inverse. What would the inverse of 1 be? It's not going to be negative 1 this time, because negative 1 isn't an element in our group.
It would be 5.
Why is it going to be 5?
Because when you add 1 plus 5 mod 6, you get 0.
Bingo. Yeah, 1 inverse is going to be 5, since 1 plus 5 mod 6 turned out to just give us the identity element. It's going to be 0. Do inverse? It's going to be 4. 3 inverse?
3. 2. 1.
Blast off. Yeah. Turns out 1 and 5 are going to be inverses of each other. 2 and 4 are going to be inverses of each other. 3 is its own inverse, and 0 is its own inverse. So 3 inverses itself, because 3 plus 3 will give us 0 mod 6. Or mod 6 will give us 0, which is our identity element. So in general, x inverse is always just going to be the thing you need to add to it to get up to n. So x inverse will always be 6 minus x. Mod 6. I have to throw in mod 6 in there because 0 inverse is not 6 minus 0. It's, because that would just give us 6, but it's that mod 6, so to speak. And this generalizes to, in general, in Z mod NZ, X inverse will be 6 minus N mod N. Any questions about how the group structure works? I claim this group is cyclic. Anybody find a generator for this group? Some element that if you were to add to itself over and over and over, or to add to its inverse over and over, you would get back, you would get all of Z mod 6. Okay? 5. 5? Oh gosh. You're going with the harder one. Okay, Nick proposes that 5 is going to be a generator for this cyclic group. Let's put his theory to the test. If we were to take the group generated by 5, well, let's see. We're going to start with 5. If we added 5 to itself, what are we going to get? Mod 6. So since we're adding to it, since we're adding to itself mod 6, we'll get that 5 added to itself mod 6 is going to give me 4. If we were to add 5 again, mod 6, what would we get? If we were to add 5 to itself again, mod 6, or to 3 mod 6, what would we get? Turns out, if we add 5 to itself over and over again, we get the entire group. And that's going to give us, and so that tells us then that Z mod 6Z is cyclic and is generated by 5. Are there any other generators in this group?
One.
Let's see, if we added 1 to itself, we would get 1 plus 1 mod 6 is 2, plus 1 again is 3, plus 1 again is 4, plus 1 again is 5, plus 1 again is 0. One will be another generator to our group. So group generated by 1 is the same as the group generated by 5. Yes, I know 1 generates it in the opposite order as 5 does. It would go 1, 2, 3, 4, 5, 0, and not 5, 4, 3, 2, 1, 0. But the order in which we get the elements doesn't matter. It still will produce the entire same set of elements, which is the entire group. So 1 and 5 are both going to be generators. By the way, here we could have just used this property that we talked about last time that says the group generated by any element A will always be the same as the group generated by A inverse, to say since 1 and 5 are inverses of each other, if 5 generates the whole group, 1 will also have to generate the whole group. Let's try 2. What would be in the group that's generated by 2? We started out by adding 2 to itself, mod 6. What would we get? Right?
4.
2 plus 2 is 4. Huzzah! What would we get if we added 2 again to 4, mod 6? 2 is not going to generate the group. It's only going to give us 0, 2, and 4, the even numbers in Z mod 6Z. And because 4 is equal to 2 inverse, 4 is going to generate the same thing. What's the subgroup generated by 3? Clear these subgroups. Is there going to be any other elements in the subgroup generated by 3?
0.
It's going to be 0. 3 plus 3 is 0 mod 6. And that's it. And finally, we need to check what's in the subgroup generated by 0. Just 0. Identity element only ever generates itself. So that's kind of interesting. 1 and 5 generated Z mod 6Z, but 0, 2, 3, and 4 did not. I wonder if there's any sort of special relationship that 1 and 5 have with 6 that 0, 2, 3, and 4 do not. So, anybody notice anything like some properties that 2, 3, 4, maybe ignore 0 for now, but 2, 3, and 4 have with number 6 that 1 and 5 do not, or vice versa?
They have a common multiple.
They all have common multiples of 60 would be a common multiple of all of these.
I mean, 1 and 6 and 5 and 6 are relatively prime.
Relatively prime, like the word you're looking for is common factor.
Yeah.
1 and 5 have no factors in common with 6 other than 1 and -1, if you want. But 2, 3, 4, and 0 are 2, 3, and 4 all do have common factors in common with 6. Namely, 2 and 6 have a common factor of 2. 4 and 6 have a common factor of 2. 3 and 6 have a common factor of 3. 1 and 5 are relatively prime. To 6. And relatively prime, the easiest way to describe it is their GCD is 0. Or not 0, 1. They have no common factors, no common divisors greater than 1. And in general, we're going to see this, we're going to actually prove this later in this packet. This is always going to be the case for Z mod NZ as a group under addition. That is always going to be generated by any element n in the group where n is, or any element k where k is relatively prime to n. In general, Z mod NZ will be generated by any k with GCD of k and n equal to 1. Any value k that is relatively prime to n. Okay. These people outside are going to get a stern look. I didn't really give a very stern look, but so in general, 6 is generated by Z mod 60 is generated by 1 and 5. It's going to turn out to be the case. That's because 1 and 5 are relatively prime to 6, and Z mod NZ as a whole will always be generated by any value k with GCD k as well. I claim no matter what n we choose, we can always find at least one value k that will generate it. That will be relatively prime to n. Which integer is always going to be in Z mod NZ and will always be a generator?
1.
So, since 1 is always such a k, Z mod NZ is always cyclic. And unlike the integers as a whole, Z mod NZ is our first example of a finite cyclic group. A cyclic group, a group that's generated by only one element, but also only has a finite number of elements to it. Any questions about Z mod NZ? It's a additive group. So what about under multiplication? Will Z mod NZ ever form a group under multiplication? I think I see you shaking your head.
Well, for one, we always have zero, right?
Oh no, we have 0. And what's the problem with 0?
If anything multiplied by zero is still zero, so there's no like counters.
Yeah. Z mod NZ will never be a group under multiplication because 0 is always in there and 0 will never have a multiplicative inverse. Mainly because the identity element would have to be 1, and 0 times anything will never give you 1, even mod n. And so Z mod NZ is never going to form a group under multiplication for pretty much the same reason that the integers as a whole don't form a group under multiplication. The fact that 0 is lacking an inverse. But it does sometimes form a group if we take away 0. Okay. Let's take a look at a couple examples. Let's say, what happens if we take away 0? So Z mod 5Z is going to be 0, 1, 2, 3, 4. I'm going to ask the question, is this a group under multiplication mod n? Or mod 5, I should say. And let's also look at Z mod 4Z. Is this a group under multiplication mod 4? Your job is to find out if either one of these form a group. Go ahead, take a couple minutes. If you feel comfortable doing so, you can talk to your neighbors and see if you can determine if either one of these is going to form a group. This one mod 5, this one under multiplication mod 4.
Are we taking zero out, or?
We're taking 0 out. I totally forgot to take 0 out. If we were to just include 1, 2, 3, 4 for Z mod 5 Z star, and if we were just to include 1, 2, 3 for Z mod 4 Z star, spoiler alert, one of these is a group, the other one isn't. Find out which one. And see if you can determine a general pattern for what you think. Under which conditions, well, if we take out 0, will Z mod NZ form a group under multiplication? Go ahead and think about that. Here's another hint. Closure and associativity will work out for both of these examples. So try looking at identity and inverses to see which does and which does not form a group. are working very quietly. What are you all doing? Everybody else is being boring and being silent. So I thought I'd come back here and check out what you all are doing.
We're,
I just
and
find that
then
it's
not
not
the
very
time
simple.
that
It's
just
like-
get it
If
set.
you multiply
Yeah.
2 times 2, you get 2 more, you're gonna say 0 mod 4.
I just realized something is under addition for times.
It is for,
Tough one.
it's under addition. Now, we have a different operation.
I'm stuck on the
So,
what you got.
What did you say your
First one,
mod 5
mod
Z's
five.
are,
So
your
one
multiplication
is
and,
one. Because 1 plus 1 plus 5 is 1. Both, and then
I think that'll work, because anything
2
times
and
1
3 are
mod,
right till there's
it
inversions.
will always just still be the
2
same
and 3
thing.
is 6.
Four
Mod
is
five
inverse
is
of
1.
one top.
What can you multiply
Which is
1
IG, but then
4 by,
4.
say, mod
Like,
5?
I
That'll get you to 1.
I just
And
need to
then
Google
ditto with 1, 2, and 3
16.
mod
So the
4,
first one is
and,
I just had
second
to-
one.
Yeah,
Oh,
wait,
four
I need
times
multiplication
four
of
is
1,
four.
5, 2, 3,
4 times 4. I was just doing it. I was only
Isn't that the
multiplying.
inverse? Wait,
4 times 4
4 is inverse.
So,
4 times 4 is 16, but like,
Okay, so the first one is inverse then.
16 sounds,
oh, but that's what we wanted. Oh, dude.
gadzooks.
But then we can't find an inverse for 2 or 3, or 3 and 3 is its own inverse.
And then the next one doesn't work because
So 2 doesn't work.
2 times 2 is 0.
what's the third one say?
It does not.
So what are all the inverses?
So for the first one,
Here's
it's
the
1
other.
inverse is 1.
Yeah.
2 and 3 are inverses of each other. And then 4 is its own inverse because you don't have to just stop at 6, you can go all the way up to.
Wait, but so yeah, 2 times 3 is 6 mod 5
Is 1.
is 1. Oh, yeah.
And then bring that
That's
to-
what we want.
Funny how that happens.
But what's the pattern?
Oh, it's because it's a unit. They can't get it to my 1. That's why I think it
That does make sense.
So your claim is,
That does, yeah.
it doesn't work if it's even, it does at the top?
Yeah.
I'll give you a hint. If you were to do this with Z mod 9Z, it wouldn't work.
So square number?
If you were to do this with Z mod 15Z, it wouldn't work.
So, this is illegal.
It's illegal.
Oh, it's,
You're thinking-
it's a factor thing again.
You're thinking the right way, but not quite there yet. So let's come back together.
Whatever.
Yeah, but that takes away all the fun.
I'm still trying to figure it out in my brain.
So let's talk about this as a group, because I think you've all had some good thoughts.
A group.
Ho-ho! How about the non-zero elements of Z mod 5Z under multiplication? What's going to be our identity element?
1.
It's going to be 1. In fact, it's going to be 1 for both of these. So, in Z mod 5Z, what can we multiply 1 by that will give us 1? How about that? What can we multiply 2 by that will give us 1? Don't say a half. 2 times 3 is 6, which mod 5 will give us 1. So I think 2 inverse will be 3. And then 3 inverse will automatically have to be 2. And so finally, is there anything we can multiply 4 by mod 5 that will give us 1?
4.
It's going to be 4, because 4 times 4 is 16, which when we mod out by 5 will give us 1, since 16 divided by 5 is 3 remainder 1. So Z mod 5Z, non-zero elements, under multiplication, forms a group. How about in Z mod 4Z star? Becca, what can we multiply 1 by mod 4 that will give us 1? Someone help her out. What can we multiply 1 by that will give us 1?
Is it just one?
Indeed. Mod 4, mod 5, mod anything. 1 times 1 is always 1. What can we multiply 3 by that will give us 1 in Z mod 4Z? If anything. What? 3 times 3 is 9, which when we mod out by 4 is 9 divided by 4 is 2, remainder 1. I like it. So 1 is its own inverse. 3 is its own inverse. What can we multiply 2 by that will give us 1?
One half.
All right. Thanks, a smartass. What else? Let's see. If we multiply 2 by 1 mod 4, we will get 2. If we multiply 2 by itself mod 4, we get blah. If we multiply 2 by 3 mod 4, we get 2. 2 doesn't have an inverse, and in fact, 2 times 2 isn't even in the group, isn't even in the set. I lied to you that they both have closure. The second one does not.
Oh, that's right. Oh,
So 2 times x mod 4 is not going to be equal to 1 for every element x in z mod 4z star. So 2 has no inverse. What's that?
We just feel very, very betrayed. We're not over it.
I'm going to lie to you many more times over the course of the semester. I've already in fact, you know, when I said z mod nz is just the number 0 through n minus 1, that's a lie. Technically, they're infinite sets of numbers, but we'll get to that in like a couple months from now when we talk about quotient groups.
This goes back into why.
Now you're learning something. Z mod 5z is not a group under, or is a group under multiplication if we take away 0. Z mod 4z is not. Why is that? I'll give you a hint. If we were to do z mod 15z under multiplication, taking away 0, that's not going to be a group. If we were to do this with z mod 7z, take away 0 under multiplication, that is a group. Here's another one. Z mod 2z under multiplication, mod 2, is a group. In fact, that's the trivial group because it's just the single number 1. And the only group operation you can do is 1 times 1 is 1.
Any group where the number you're modding with is prime will be a group.
Bingo. Z mod nz, if you take away 1, will be a group under multiplication if and only if n is prime. So that's why it works for 5, it works for 7, it works for 2, but it doesn't work for 4 or 15. Whoa, Dr. Gerstle, you just spelled if weirdly. If doesn't have 2 F's in it. So if is shorthand for if and only if. What does if and only if mean in this context?
That the two statements are equivalent and you can swap them for each other.
They're logically equivalent, meaning if one is true, the other is true. If one is false, the other has to be false. So if n is prime, then this is a group. If n is not prime, then this is not a group. If and only if is kind of a way to encapsulate, it works both ways. And if and only if is kind of a long to write out, so you often just write it as IFF. But if you ever see me write IFF, that just means the thing before it and the thing after it are logically equivalent. If one is true, the other is true. If one is false, the other is also going to be false. So if you want to make a multiplicative group mod n, if your n is prime, you can do it easily. Just take away 0. If n is not prime, you're out of luck. Actually, that's another lie. Turns out that if you have an n that is not prime, you can still form a group under multiplication mod n. You just have to take away more than 0. And it turns out all you have to do is to take away everything that is, you just have to take away everything except the numbers that are relatively prime to n. And this is going to be called the group of units, mod n. So in general, U of n is the group of units, mod n, or the unit group, mod n. And the elements of this group are just going to be all of the integers between 0 and n minus 1 that are relatively prime, that have whose greatest common factor with n is going to be 1. So as a set, it's just going to be the set of all k such that k has to be between 0 and n still. And also that the GCD of k and n is equal to 1. That the greatest common divisor, the greatest common factor that your k and your n have is 1. So that's your set. And then the group operation is going to be multiplication mod n. So let's do an example where we want to look at the group of units mod 10. 10 is not a prime number, so it's not going to, so we have to take away more than just 0. So we're going to have to take away all of the integers that share, from 0 to 9, that share a common factor with 10. 0 is out because 0 is always out. Do 1 and 10 have any common factors other than 1? 1 is allowed to stay. How about 2 and 10? Do 2 and 10 have any common factors greater than 1? Yeah, 2 is, in fact, is itself a factor of 10. So the GCD of 2 and 10 is actually just 2. So 2 is out. Which, by the way, since 10 is an even number, we can immediately eliminate all even numbers from this list because they'll have a common factor of 2 with 10. Do 3 and 10 have any common factors greater than 1? Do 5 and 10 have any common factors greater than 1?
5 is.
5 is. So 5 goes bye-bye. 7 and 10? 9 and 10? Pro tip, group of units mod n is always going to contain n minus 1 because n and n minus 1 will never have any common factors greater than 1. So it turns out this group of units mod 10 only has 4 elements. 1, 3, 5, or 1, 3, 7, and 9. How about we draw a Cayley table for this group and make a multiplication table that looks nothing like the multiplication tables you grew up with? So we have 1, 3, 7, and 9 are elements. Do we have an identity element in this group? I said this is a group, so the answer is yes. Good job, Dr. Gersel, on answering your own question. What's the identity element of this group? What is our multiplicative identity mod 10? The thing that if we multiply by anything else mod 10, we would just get that other thing. It's going to be 1, which tells us automatically we can fill in the row for 1 and the column for 1 very quickly. 1 times 1 mod 10 is 1. 1 times 3 mod 10 is 3. 1 times 7 mod 10 is 7. 1 times 9 mod 10 is 9. And ditto going down this way. 3 times 3 mod 10. 3 times 3 is 9, which is totally okay. Mod 10. It can just be 9 mod 10 is just 9 mod 10. 3 times 7 mod 10. If we were to take 3 times 7 and then divide by 10, what would the remainder be? It's going to be 1. What's the last entry in this row? It's going to be 7 because if we believe Dr. Gerstle that this is a group, and as you all should have proved by now in homework 2, in every row of a Cayley table of a group, every group element appears exactly once. This better be 7, because 7 is the only one missing. And it turns out if we take 3 times 9 is 27. Hey. And 27 is my favorite number. And we take 27 mod 10, we are going to indeed get 7. 7 times 3 is 21, mod 10 is 1. 7 times 7 is 49, mod 10 is 9. 7 times 9 is 63, mod 10 is 3. 7, 3, 1, boom. There's our Cayley table. So when you go tell people, what did you do in your math class today, tell them you did things like, oh, I made a times table where I said 7 times 7 is 9. See what they think of that. So Z mod NZ under addition and the group of units mod n under multiplication will both be examples of abelian groups, meaning the group operation works the same both ways, and that's mainly because integer multiplication and addition is commutative. So a plus b mod n is the same as b plus a mod n. A times b mod n is the same as b times a mod n. And so these are going to be nice abelian groups. Which, by the way, check this out. Notice anything interesting? Here's something that's always going to be true for the Cayley table of an abelian group. Notice anything about this dotted line in the table? Dave, why are you eyeing?
Well, took me a second, but they're mirrored on
Yeah.
that line.
It's going to be symmetric, and that just basically comes from the fact that like 7 times 3 is the same as 3 times 7. So the fact that the operation is commutative means that if you were to take the top right half and fold it onto the bottom left half, they would match up perfectly. And that's always going to be true for the Cayley table of any abelian group. If your group's not abelian, then this won't happen. It's kind of a nice, cool property. Sort of looks like a symmetric matrix. If this was a matrix, you could take the transpose of itself and it would still be the same thing. Okay, is this group cyclic? We said Z mod NZ is always cyclic under addition mod n. How can we check to see if this group is a cyclic group or not? All right. How disappointing.
Try to find an A that can mod through and give you those 4 values.
Yeah, let's just brute force it. you only have 4 elements to check, we can just look at what is the subgroup generated by each of these 4 elements. If any of them give us the whole group, then we're golden. All right. What is going to be in the subgroup, or in the group generated by 1? We're going to have 1, and if we multiply 1 by 1, we'll get 1, and if we multiply 1 by 1, we'll get 1. But we can also multiply by 1 inverse, which is 1. And so if we multiply that 1 by 1 inverse, we'll get 1. And if we multiply by 1 inverse again, we'll get 1. And it's a trivial group, just a single element. So 1 is not going to be our generator in the group of units mod n, because it was always our generator in Z mod nz under addition, but it's never going to be our generator in Z mod nz under or in the group of units mod n. Unless you're taking the group of units mod like 1, and it's the only element in your group, and in which case that's a stupid example. How about 3? If we multiply 3 by itself, mod 10, what are we going to get? Hey, it's almost as if I drew the Cayley table, so that could help us out with this. What is 9 times 3 mod 10? What is 3 times 7 mod 10? Hey, how about that? So group 10 is the group of units mod 10 is a cyclic group, and 3 is a generator. How about 7? If we were to take 7 times itself mod 10, times 7 mod 10, times 7 mod 10. Hey! Oh wait, 3 and 7 are inverses of each other, so they had to generate the same group. How about that? Finally, let's look at 9. What's 9 times 9 mod 10? Oops. So 3 and 7 are both going to be generators, but 9 is not. And this time, we don't have a nice trick like, it's going to be a generator if it's relatively prime to n. Well, they're all relatively prime to 10 mod, or they're all relatively prime to n mod n by definition of the group. So it's a little bit harder in the group of units mod n to see which elements will generate it, which ones will not. And here's another plot twist. Sometimes the group of units mod n is cyclic, and sometimes it isn't. U10 happened to be a cyclic group because I purposely picked one that'll be cyclic and have a small enough table. But a group of units mod 8, check it out for yourself. It ain't cyclic. Any questions or comments about any of these examples? Okay, so that's it for the fun part of cyclic groups, where we look at a bunch of examples and go ooh and ah. Next week, we're going to prove some big old nasty theorems relating to subgroups of cyclic groups in general. And ultimately, we are going to prove the fundamental theorem of cyclic groups, which says something about if you're looking at a cyclic group of order n, and it has to have a unique subgroup of every order that is the divisor of n, and blah, blah, blah. We're going to prove a lot of cool properties about cyclic groups. But these are kind of our nice examples of finite abelian groups that we'll be using as examples throughout the rest of the semester. Have a good day, everybody. See y'all on Monday. Have a good weekend, everybody. See y'all on Monday.
Thank you.